Hello students, in this video lecture we are going to discuss an important topic of theory of computation, that is push-down automata, which is also abbreviated as PDA. Now a push-down automata is a way to implement a context-free grammar in a similar way we design DFA for a regular grammar. uh, DFA can remember a finite amount of information, which we already see, but a PDA can remember an infinite amount of information. Basically, a push-down automata is a finite state machine plus a stat. That is, if we include a stat in the finite state machine, then it is considered as push-down automata. Now, the important components of PDA. There are basically three components of PDA: input tape, finite control, and stack. This you can clearly see in the next diagram like this. Input tape is there, then a finite control is there, and a stack is there. Um, Now what are they working? Now input tape. The input tape is divided into many cells or symbols. The input head is read only and may only move from left to right, one symbol at a time. Finite control. The finite control has some pointer which points the current symbol which is to be read. Stat. The stat is a structure which you already read in the data structure and algorithm. The stat is a structure in which we can push and remove the items from one end only. It has an infinite size. In PDA, the stack is used to store the items temporarily. Now, these three components you can see in the diagram of PDA. There is an input tape. The finite control is there, which takes the symbols from the input tape and doing some push and pop operation with the use of a stack, and after that the finite control gives the result in the form of acceptance or rejection of the string. Now, a PDA can be formally described as 7 tuples. Now, these are the 7 tuples. Q is the capital Q is the set of states. Sigma is the set of input symbols. Tau is the set of push down symbols which can be pushed and popped from a stat. Del, which is the transition function which maps Q cross sigma union epsilon cross tau, and it produces in the output is q cross tau star, which is the combination of push down automata symbols. Now the q naught is the initial state, z is the initial push down symbol which is initially present in stack, f is the set of final states. Now, with the use of these 7 tuples, we can easily describe the PDA. Now, the transition in a PDA from a state Q1 to a state Q2, labeled as this: A comma B produces C. So, what does this mean? If from a Q1 to Q2, this type of transition is there, this means that where A is the input symbol, now B is the stat symbol, and C is the push symbol. This means that at state Q1, if we encounter an input string A and top symbol of the stat is B, then we pop B and push C on the top of the stack and move to state Q2. Push down automata acceptance. Now there are two types of acceptance. One is final state acceptability and the other is empty state acceptability. Now first we see the final state acceptability. In final state acceptability, a PDA accepts a string when after reading the entire string, the PDA is in the final state. From the starting state, we can make moves that end up in the final state with any state values. So at last we can go to the final state for this type of acceptability. For a PDA with 7 tuples, the language accepted by the set of final state is this. Now this is the general format. Like for a string, let w is there, and this is the q naught is there, then w is the string, and z is the push down symbols. Now after with doing some transitions, we finally move to the state q with the string consumed, and finally we reach to the final state where q is the final state. Now let us discuss an example of final state acceptability. We need to construct a PDA that accepts 0 to the power n, 1 to the power n, such that n is greater than equal to 0. Now we first need to make the language of this. Now the language accepted by this is epsilon, because 0 is there. Now 0 1 double 0 double 1 triple 0 triple 1. Now we can see that here the number of zeros and number of ones have to be same. Initially we put a special symbol dollar into the empty stack. Then at state q2, if we encounter input 0 and top is null, we push 0 into stack. This may iterate. If we encounter input 1 and top is 0, we pop this 0. Then at state q3, if we encounter input 1 and top is 0, we pop this 0. This may also iterate. If we encounter input 1 and top is 0, we pop the top element. If the special symbol dollar is encountered at the top of the stack, it is popped out and it finally goes to the accepting state Q4. You can see in the diagram that Q4 is the accepting state, and at last we reach to the accepting state for this type of acceptability. Now the second is empty state acceptability. Here a PDA accepts a string when after reading the entire string the PDA has emptied its stack. For a PDA with 7 tuples, the language accepted by the empty stack is this. Suppose W is the string, then Q naught is the initial state, W is the string, and Z is the push down symbol. With some transitions, we reach to to state Q. Then the string is consumed, and finally we get the empty state in the stack. Mm, Now let us discuss an example based on empty stack acceptability. Now design a PDA for accepting the language 0 to the power n, 1 to the power m, 0 to the power n, such that m and n is greater than equal to 1. In this PDA, n number of zeros are followed by any number of ones, followed by n numbers of 0. Here the logic for design the PDA is push all zeros onto the stack on encountering first zeros. Then if we read 1, just do nothing. Then read 0, and on each read of 0, pop 1 0 from the stack. Now in short, you can analyze that first zeros are being pushed into the stack, and the last zeros, after encountering each 0, we can pop out every 0 from the stack. So at last we reach to the empty stack. Now, let us discuss in a more elaborative form. You can see a string is there with 00 triple 1 00. Now first, after encountering 0, push it onto the stack. Then after encountering second 0, push it onto the stack. So there are two zeros present there. After encountering 1, skip 1. Then second one, after encountering second one, skip 1. The same procedure has been adopted after encountering third one. Now as soon as we encountered a 0 after the 1, so after each 0 we need to pop that the 0 from the stack. So after encountering first 0, we pop first 0 from the stack. After encountering second 0, we encountering the last 0 from the stack. So at last we reach to the to the empty state. This above PDA was accepted by the entering into empty state. Now equivalence of acceptance by final state and empty state. If the language equal to np1 for some PDA p1, then there is a PDA p2 such that L is equal to lp2. That means the language accepted by empty state PDA will also be accepted by final state PDA. Also the reverse is also true. If there is a language L equal to lp1 for some PDA p1, then there is a PDA p2 such that language is equal to np2. That means language accepted by final state PDA is also accepted by empty state PDA. So the language accepted by final state PDA is accepted by empty state and vice versa is also true. That's all about PDA. Thank you for watching this video.